I'm Doug Clinton, co-founder and managing partner at Deepwater Asset Management, and this is the Deload podcast, where I interview founders and builders of companies who are building products that will change how we live. Today, I talk to Jack Kendall. He's the CTO of Rain AI, which is one of our portfolio companies at Deepwater. Jack and I talk all things AI. It's a 401 level course on what is happening right now in generative AI, how Rain and the chips that they are building will ultimately help accelerate the progress in AI, and Jack's prediction on when we will achieve artificial general intelligence. So now here is Jack Kendall from Rain. All right, Jack, good to see you as always. So I wanted to start, and I think you're in kind of a really cool, unique position to speak to this. If you kind of think about the history of AI, the evolution of AI over the last decade or so, it's gone very much from sort of this like research world where things were happening, in labs, kind of in very concealed environments, to now even in just really the last year with Chat GPT, kind of this wide open experiment in the real world. And I'm curious how you think about, because you still have a very strong research focus at Rain, how do you think about that balance between the research side of AI and the commercialization of it?
That's a great question. And so I'll say, my philosophy and the philosophy of Rain is that we have a really strong focus on fundamental research. And it's built into our DNA. It's helped inform a lot of our roadmap and the trajectory of Rain. Now, my sort of inspiration for this and kind of like the guiding star organization for me has always been Bell Labs, actually. And
Hmm.
Bell Labs, this is where the transistor was invented, among many other important inventions. But they really showed how to, and that it was possible to do research in basic science and translate those advances from the world of basic science to commercialization and to really impactful technologies like the transistor. I think there are other examples of organizations like DeepMind, to be honest, comes to mind.
Yep.
DeepMind really made some incredible innovations in reinforcement learning. They were the ones who really showed how to combine reinforcement learning with deep learning for the first time. And, they were obviously able to bring to commercialization incredible tools of particular note, AlphaFold. I think, AlphaFold made some a modest splash in the scientific community, but I think it's been, undervalued as what I really think is one of the most important technological innovations of the 21st century. So that's another really great example. And this is a philosophy that we like to take, my research on essentially equilibrium propagation is an example of this, but how to perform training in deep neural networks in completely analog substrates. This is an algorithm that was invented by one of Yoshua Bengio's students and an engineer at Rain whose name is Ben Sellier. And they really laid the seed of this innovation. And what Rain did and what I did at Rain is take this algorithm, which primarily was working on software networks, and show how you can actually extend that to train physical systems and to perform what is almost like a self-contained physical learning system. And this has been a really big part of our research, and we're pushing this towards commercialization as well. Although this is on a longer time horizon than our immediate commercialization endeavors. But that's sort of an example of how things work at Rain.
Yeah. I think the Bell Labs comparison is such a great one. I mean, I think of Claude Shannon and information theory and all the incredible things came
Yeah.
from Bell Labs. It's cool to think of a world like that. And even I think Google was inspired, sort of the 20% time, if I remember, was maybe inspired by Bell Labs. Do you think that's kind of the right comp as you think about building an organization that thinks about this, that, maybe it is whatever, 20% time arbitrarily, that is the right amount of resources to put toward this forward-thinking research versus what's ready to go today?
Yeah, I think I think it depends on the scale of your organization too, as
Hmm.
well. Rain, we're 35 people or so. And so, we have a product to get to market. And so I think for us, it's probably maybe closer to 10%.
Yep.
And we have but I think that the 10% that we have is a really focused team that is dedicated towards this type of frontier research. Whereas maybe at a larger organization like Google, you can have more resources once you've got, revenue coming in and, a stable baseline for that. But yeah, I think it's organization dependent. But yeah, I think especially in the AI space, you've seen it with OpenAI as well. Like an emphasis on fundamental research can pay massive dividends for eventually coming to commercialization. And, the difference between who won with ChatGPT, right? Who got to that level first? I mean, maybe that was a matter of months, right?
Yeah.
And it was just a little bit of extra resources put into one organization versus the other. So,
Yeah, I mean, being first is a huge advantage in so many different ways, and then it fuels more research. I mean, it's a
yeah.
cyclical thing.
And it fuels more data more importantly. Like
Hmm.
that's the biggest advantage that came out of, OpenAI getting to ChatGPT first was
Yeah.
that all of a sudden they had millions of users interacting with these systems and the competitors didn't, right?
Yep.
And I mean, I think you'll see that, and we have seen that data is everything, right? The models, once the transformer architecture was invented, you know, model architecture didn't really matter that much other than scale compared to the quality and the amount of data that you have.
Yep. If you think about what we're talking about now, in the context, you mentioned OpenAI, and there's been some crazy things happening there with
Oh
Sam
yeah.
Altman going and back. We don't need to recap the whole story. I'm sure everybody's probably aware of it.
Yeah.
But the fundamental question, I think, does in some ways circle back to this idea of research and maybe how far along they are on the path to, AGI. Do you think that they are maybe closer than the world realizes? Was that what sparked this whole thing?
So I can give you my thoughts on this. They're going to be a little nuanced and maybe require a little bit of an explanation and some background. So bear with me here.
Hmm.
But here's what I think. Um, this is worth noting. This is all speculation at this point. Yet all anybody can do right now is speculate because we don't know exactly what happened. Um, but for context, not everybody is a believer in deep learning. And I know that that seems, more and more a little, um, I don't want to say ridiculous, but maybe not entirely true. I think we've certainly seen the power of deep learning, especially over the past year. But many people remain skeptics that it will bring us towards, quote, true intelligence. And of course, what they mean by true intelligence they keep moving the goalposts.
Changing.
Yeah. But there have been two good arguments that I think have that support them, that they have to support this idea that deep learning maybe won't take us towards true intelligence. And that is the first one is that deep learning can't do causal reasoning. It's only doing pattern recognition. And I think this has been, my opinion is that this has been demonstrated to be incorrect. That deep learning is capable of doing causal understanding. And I think you wouldn't be able to have a conversation with ChatGPT if it didn't have some level of causal reasoning or a causal model baked in to the network. And, to give an example of this, like if you go and you say to ChatGPT or show it an image, maybe of a girl holding balloons, and you say, what will happen if I cut the strings? It will answer that the balloons will fly away, right? And that requires a causal model of the world in order to do that. Now, that's just an anecdote, and you can construct many other anecdotes about this. But as far as the actual research to support this, in 2018, DeepMind showed that using reinforcement learning, if you have a reinforcement learning agent, they are actually able to extract causal information from their environment. And the reason that they're able to do this is because they can perform interventions. They can do kind of like almost experiments, and they can influence the data that's incoming to them and learn causal information as a result. So I think that that sort of you know, argument from the anti-deep learning crowd is no longer true. And these models do now have some level of causal reasoning. The other big one is symbolic reasoning. And this is the one that I think is relevant to OpenAI right now. The argument is that deep learning models can't do symbolic reasoning like humans do symbolic reasoning. And I'll give you an example of what I mean by this. Let's say that, you know, I know from my, you know, from the data that I've been taking in from a child, I have learned that all dogs are mammals, right? And all mammals have fur. So I know these two facts and I can reason about them. And for instance, what I can do is I can say, my friend's dog, maybe, which maybe I've never met before or I've never seen before in my life. I immediately can deduce that that dog has fur from these two statements. And this is just a very simple example of using symbolic reasoning and relationships between the sort of internal symbols that I have for dog, for mammal, and for fur, right? Deep learning models, modern deep learning models, they can't really do this. They're kind of very bad at this. The pinnacle, I think, of this is mathematical reasoning. In order to do, and you've noticed maybe that ChatGPT can't do math. In particular, it's
Yep.
very poor at doing math. And it's because it lacks this symbolic reasoning. I believe that the breakthrough that OpenAI is working with right now, people are referring to it as Q-star, involves mathematical reasoning. And in particular, I think this is an indication that symbolic reasoning is being solved. So the implications of this are quite huge. Even if this model is doing middle school arithmetic, the fact that it is doing symbolic reasoning in mathematics at all means that there are no more missing pieces, right? You have all the ingredients that you need for and we're still a long way away from human level intelligence, but the type of intelligence that we have, maybe we're closer than people think. And it might just be a matter of scaling these models into data sets. And at that point, it's just an engineering challenge, right? So that's my take, that's my read on why Ilya or the board or the people with more knowledge than I do might have reacted like that.
So if that's true, would it be fair to say that we are on the verge, I guess, of AGI, even if the verge means we're still, let's say, 10 years away or 15 years away, but we've fundamentally got, to your point, all the pieces of it, and we should sort of assume that, hey, the probabilities of us getting there are pretty high.
So, I've said for many years now that I think that AGI is going to be achieved in 2025. And we're getting closer and closer to 2025, and my prediction has not changed. I still believe that we're going to hit it in 2025. And this is like, I wasn't sure when I knew that the last missing piece was simple processing. The combination of what's called the symbol grounding problem and the binding problem as it refers to like neuroscience, but these problems both I believe are on the verge of being solved or perhaps may have already been solved at the research level. And just to give some more concrete example to support this, there already has been research that shows that transformer architectures, which is what powers ChatGPT, they are capable of doing some symbolic reasoning. So some symbolic reasoning tasks can already be solved with transformers, just not generally. And you can actually extend these capabilities by modifying the transformer architecture with things like scratch pads. But I think it's quite likely that this last piece is going to be solved quite soon. Now, as far as whether that means we're at AGI, it depends on your definition of AGI, right? Some people believe that AGI means human level intelligence. And I don't hold that. That's not my definition of AGI. That's my definition of human level intelligence, right? I think we're a long way away from human level intelligence. But what I think of as AGI is I have a few things that I have written down here that I think define AGI. So I define AGI as a single network architecture that can, in principle, learn any combination of data modalities, for example, speech, vision, and language. So we already have that check mark. Use prior experience to learn new things rapidly. I think that's part of causal understanding. And reason about things or perform tasks it hasn't seen or done before. And I think that's what really requires symbolic reasoning. So if you have these three things, I think, it can do, you can maybe tell a machine to go do the dishes for you. And, I think robotics is actually something that's lagging behind the rest of these things. But, in principle, that would become possible. It would be able to understand and execute on a task like that. I think that's what makes a general intelligence.
I think that's a great definition. And so, if we have had this breakthrough, then on the symbolic reasoning side, and we do get to your definition of AGI by 2025, that doesn't necessarily mean that the world would look maybe a lot different than it does today, does it? I mean, I think that's the concern when people think about AI, right? It's like, oh, artificial general intelligence, jobs are gone, and now then we get super intelligence, and we can get into that whole train of thought. But as you think about it, what does that mean in 2025?
So I think it means, it'll have the same impact that ChatGPT had when it launched,
Hmm.
which is that people are going to be like, oh, damn, this is real, you know. But as far as actually having an economic impact, I think that some things have certainly been economically impacted, and people are making decisions based on predictions of how things will change. But I do think that it takes time for a technology like this to percolate through society. And hopefully, enough time for us to adequately prepare. And this is, I think, been a very good wake-up call for governments and people in general, because, I've been advocating for a long time that we need to do more to prepare for
Hmm.
this. I think I'll mention Andrew Yang. I think he was, I don't agree with him on all of his views, but I do have a huge amount of respect for him because he was really the first major politician to start pushing preparation for AI, and automation. That's definitely going to be coming. So I don't know exactly what's going to happen when we have these general models, but I suspect that they will take some time to be integrated into society in meaningful ways. Obviously, you're going to have automation of menial tasks. Um, like you're going to now have the ability to, have a system that knows your workflow and automates, maybe can reply to emails and schedule appointments for you, things that you don't have to do like that. But the real implications of this technology, I think we're not going to see until significantly after 2025 when the breakthrough happens.
And if you think about society and the government, are there any big things that stand out to you that you think they should be doing or legislation that should be talked about to prepare for this?
I think you have to put in place legislation that will protect people who have lost their jobs due to this technology. And I think that should be funded by the gains that have been made by the corporations that are doing the automating, right? That's my personal belief. I know some people might not agree with that, and that's totally okay. But I think that you have to do something to protect the people who are going to lose their jobs, um, at least in a temporary sense, because there will be job losses coming.
Hmm.
I don't think we even know necessarily where they're going to get hit hardest. We thought that trucking was going to be hit hard, but it wasn't really, at least not yet, for reasons that, some people predicted for sure, but other people did not. And it's that self-driving is harder than we thought. So maybe that will be solved with these large language models. Maybe now you'll have systems that have world models, that understand that a bag, in the middle of the road is not going to destroy your car and you can just drive over it as compared to a brick in the middle of the road, which maybe you want to avoid, right?
That makes sense. Yeah. And so if we think that AGI maybe is the defining topic around AI in 2025, what do you think it is for next year? What's the stepping stone to there?
I think that we're going to see mathematics happen.
That's the big one.
I think it's going to be mathematics. Obviously, like multimodality is already a solved problem in that you can have language and vision integrated within the same model. And people have shown that they are capable of building world models, these large language models. So they have some idea of how the world is organized. And it's not just, I also want to emphasize, to the viewers who may be watching that there's a widespread belief that, ChatGPT is just kind of fancy autocomplete. And I don't disagree with that. I disagree with the word just, right? The amount of knowledge and understanding, like actual understanding, that it requires to do this autocomplete, there's a reason that it was not possible until very recently, right? This is an extraordinarily hard problem. And if you want to do if you want to answer a question like, you know, where is even a very simple question like, where is Mexico in relation to the United States? That requires you to have a spatial understanding of the map of our world, right? And there are ways that you can probe that and you can know for sure that it's not just memorized all of this data because you can ask it questions that are certainly outside of its training data. And it may not seem like that's possible to do, but all you have to do is, to understand this, all you have to do is say, stack a bunch of really unlikely things on top of each other in a long chain, right?
Mm.
So for image generation, I'll give you an example. I'll say, please generate an image of an elf on top of the Empire State Building wearing a crown, which is surrounded by flames, playing metal guitar, with stars twinkling in the background. And it will do it, right? It will do it. And you can chain together as many unlikely things as you want, and it will generalize. And for certain, that image was not in its training data. And so it hasn't memorized its training data. It has built a model of the actual, what we call is like the data generating process. It's really a manifold or like a geometric object that is sort of underlying the space of data if you want to, be mathematical about it. But it's not just autocomplete and it's not just memorizing things. So I know that was a little bit of a little bit long-winded, but I think that's
I th-
important to convey.
I think it's super important too, and it's if you use any of these tools, I think in great depth to really do something. Like I've used a series of the generative AI platforms to actually pick stocks, and I've done a lot of testing on it, and I've built a lot of different portfolios, and they're actually beating the markets in more than 65% of the cases. So to your point of understanding, like there's absolutely some form of understanding. And when I talk to people about it, like it often goes into this thing of, well, does it understand like a human? No, I don't
No,
think it does,
right.
but it understands, to your point, what is being asked of it and how can it give you something that is a useful output based on that reasoning. And there
Right.
is a kernel of intelligence in there.
That's really the right way to think about it. It's not like a human would understand things, but there is some level of understanding, and there has to be in order for it to have the performance that it has and to be able to do the things. It's a long time ago. I talked with a researcher at my university, at the University of Florida, and he was in AI and circuits and things like that, hardware instantiations especially. And I was talking to him about like learning algorithms and, how does the brain work and things like that. And I asked him, like, how do you judge? There are so many different learning algorithms that people have put forward. Like, how do you judge which one is the best? And he just told me the proof is in the pudding. Like, whichever one gets the best performance and does the most, is capable of doing the most things, that's that's likely the closest to what the brain is doing, and it's certainly the best one. So the proof really is in the pudding here.
It is. It is. So if 2024, let's say, is kind of the year where we're talking about math and symbolic reasoning kind of coming into these models, how do you think that will change how the average person sort of experiences generative AI?
I think there's a lot for me at least. I do,
Yeah.
to be honest, I do a lot of math. So, but like, I think that there's actually a major limiting factor that you can't really ask, you can't get precise answers on things, right? Especially that involve math. And that's kind of the Achilles heel right now of these models is that they don't have a level of precision. They're, the way that they work is to generate data that's like the data that they've seen. There's no constraint on them that says that that has to actually correspond to anything in the real world. If you ask it to give you a reference on some obscure topic, it'll just fabricate, you know. And if you ask it to solve a math problem, like it'll give you numbers, but they'll be totally wrong, right? So even like a physics problem, you ask it like, I have a 100-gallon tank and, it's flowing, it has a hole in it and it's leaking water at a rate of 1 gallon per minute, right? How long is it going to take for that to drain? That might be a useful question that somebody might want actually answered. And it just won't give you a right answer to that because it can't do the calculations. And so with math, right, all of that becomes possible. There's a lot of things that are, in its level of understanding of the sciences and physics that rely on math that could be incredibly useful to lay people, which
Hmm.
are just not reliable sources of information right now. And all of a sudden, you start including symbolic reasoning, mathematics, those all become much more reliable. So
Yeah.
I think that's maybe a good example.
Yeah. In a funny way, right? Homework just got a lot easier for
Oh,
kids probably,
yeah.
but
That's a
but like
whole
it,
other
yeah, there's a
enormous.
lot of things we need to figure out there
Oh,
probably.
yeah.
Another question though, funny, like we often get asked that question, but then the next question we'll get asked, which is so much more compelling, is do you think that AI will solve a major problem like cancer, or will it create something new in physics, right? Will it make a discovery in physics, let's say? And now that it will have the ability to do mathematics, do you think that that is possible?
That's a great question. And I'll just say that like AI already has done that with protein folding.
Hmm.
I mean, protein folding was a generational problem in science, and I would argue that it was the most important unsolved problem in biology. And now that we have the ability to just to give context on like what it mean, like what does protein folding mean? Like we were basically completely in the dark as far as how the sequence of amino acids in your DNA, or the sequence of nucleotides in your DNA, or the sequence of amino acids in a protein
Hmm.
actually translated to how that protein functions, right? So we were unable to go from, DNA sequence to what does this protein do, right? How does it work? How does it function? And the thing is that how proteins function are basically entirely dependent on their shape, right? And so if you can take a sequence of amino acids or a string of DNA and predict how the protein will fold, the particular configuration and space that it will take after it's been translated, you can figure out how that protein works and
Hmm.
interacts with other proteins and interacts with other molecules. And we were completely unable to do that. Now we know. Now we have the ability to do that. And as a result, so many diseases, so many drugs can be synthesized, so many, you know, we can really, what is at the heart of biology is these are like nanomachines, right? Now
Hmm.
nanotechnology also gets supercharged, and we have the ability to start building novel proteins that don't exist in nature that are built specifically for tasks that we want to perform, right? So this is a massive scientific breakthrough that's already been made by deep learning. Now we can talk about mathematics as well. I think it'll be a little while before, because I think what we'll start with is, oh, like these systems will do like middle school level math, but reliably. And they'll be able to have like the language understanding, right? It's really the combination of all of these things that's compelling. But I think with the right data sets and time and scale, they will start being able to do what I will call university level mathematics. And they will begin to understand how to do proofs. And the thing is that even if they're 1% as efficient as a human researcher, the level of scale that you have from these systems is so extraordinary. You can just run millions of instances of these systems constantly at 100x the rate of processing that a person would be able to. I think there's a very real possibility that maybe not in 2025, but some years after, we start making major advancements in mathematics with these systems. It's not unrelated to systems like Lean, which are automated proof solvers, but I really think that there's going to be this integration between proof solvers, proof checkers, really, and systems like ChatGPT with mathematical abilities that will really, again, turbocharge mathematics.
It's so exciting to think about that opportunity coming maybe sooner, to your point earlier about 2025, 2024 being that year with mathematics, maybe sooner than people realize. And I want to bring in some of your experience now with Rain as well. You think about this world that we're talking about, the direction we're going, it's going to require a lot of compute, obviously.
Yeah.
That's the other big thing aside from data. And at Rain, you're obviously working on artificial brains. You're trying to make compute more efficient. How do you think about compute in the context of this incredible future that I think it feels like we're really on the cusp of? But do we have enough infrastructure, and how does that need to change to deliver on this?
That's a great question. So, I think that right now we've hit a little bit of a plateau, to be honest. And I think that we've seen that happen, and you know, at Rain, we've seen it coming for a long time. We weren't sure exactly when we were going to hit it, but it seems that right now is, the point where we've hit the maximum to within an order of magnitude, right? You can only sustain exponential growth for so long. And models were doubling every 3.5 months
Yeah.
over the past, 6 years. That's got to come to an end at some point. And we've essentially, with the combination of Moore's law ending, GPUs are no longer gaining, exponential price performance improvements, and the data scale infrastructure that we've built is, reached into the multiple billions of dollars. And so you can't really scale these out by any, certainly not like two more orders of magnitude. Um, so the size of these systems is not going to keep accelerating like we've seen it in the past. And so we're not going to keep getting the gains that we've seen in the past. However, there was a, what I'll think of as a major breakthrough in computation recently in hardware, right? And to put it into context, really the big limiting factor in hardware that we have right now, it's really just that brains and GPUs are nothing alike. Right? CPUs and GPUs, they are built on the von Neumann architecture, which is based around the separation of memory and processing. And so, like your memory, like your RAM, right, is located in one place. And then your CPU, or your ALU, or arithmetic logic units, they are located in another place, right, physically. And the only thing that connects them is a narrow bus, right? And in GPUs, maybe you have multiple copies of these, but it's nothing like the parallelism that we have in the brain. In the brain, memory and processing are unified. They're actually the same physical substrate. And so this really expensive movement of data in the von Neumann bottleneck, which is, this is the memory wall essentially, right?
Mhm.
Moving data, these networks are massive. They require huge amounts of data. So you have to move a ton of data from your memory into where the processing is located. And that bottleneck is, the reason why we need huge data center scale, appliances to run relatively modest neural networks by biological standards, right? If we can break through this bottleneck and do the computations inside the memory or significantly closer to where the memory is located, that is going to give us order of magnitude improvements. And that's going to break us out of this plateau that we've hit. There are indications that a major breakthrough has been made, and it's not far away from commercialization. And this is related to RAM, in particular DRAM. But if this pans out, we may see in the next few years modern LLMs like ChatGPT able to be run locally, like on your cell phone, without. And people have tried putting LLMs on cell phones, and there are some papers around this, but they're always like extraordinarily compressed versions. They're not like the full scale model. And so running full scale GPT-4 on your phone in a reasonable amount of time is just simply not possible right now. But
Mhm.
this breakthrough, we're talking about like 500x improvements in energy efficiency and latency decrease.
And when you say running on the phone, you're referring just to inference, not talking about training. That would be a totally different issue.
Training will also be impacted by this.
Mhm.
But yeah, I'm specifically referring to inference, and I mean locally, right? You can
Yep.
get ChatGPT on your phone, but it has to talk to a server, which then communicates with you. And so,
Right.
this is what we refer to as like edge. If you're in a device that either doesn't have connection to the internet or is really latency sensitive and can't handle the few hundred milliseconds that it takes to transmit data to and from a data center. A good example of this is like real-time language translation in your ear. If you have an earbud, um, and you're trying to automatically translate what somebody is saying to you in real time, that delay, the delay of talking to a data center essentially kills the application. It makes it unusable. Similar with like speech recognition. Like you talk to Siri and then, a few seconds later it gives you a response. It really degrades the quality of the interaction. If you can run these models locally on the device, you eliminate that and you get really crisp, fast latencies with no delay.
And it stands to reason too, if we see a world where we have intelligent machines, adaptive machines in the future, don't they sort of need to be able to learn on the fly? And that's going to happen on the edge, not, to your point, sending stuff back and forth to a data center.
Exactly. Like the cost of sending all of that data is really huge, especially on like wireless devices. Sending data is really power intensive and you're burning a lot of data. Data transfer is expensive as well. If you can keep that local to the device, you save huge amounts of power and data transmission costs. And also you do circumvent a lot of the issues with like privacy. You don't want to be, a lot of people don't want to be sending all of their data to Google and Facebook and Amazon and these big companies. Um, but yeah, having your data completely local is, I think, really beneficial. Um, and we want these, you know, every time you talk to ChatGPT, it forgets everything that you've talked to with it
Hmm.
about. It forgets all of your conversations. The context window is only so long, right? And you don't want to load into context all of your past conversations like every time you want to have a conversation with it. You want it to actually like learn. You want its weights to change and it to actually learn and internalize its interactions with you, I think. I think that's something that's important to people who are especially, you know, having, I think there are a lot of, especially like young people who are using these character creators and having conversations with these AI systems, and that opens a whole other can of worms too. But at least for your assistant, you want it to be able to know you. So
Yeah. I mean, to your point earlier about intelligence, I mean, intelligence is partially the ability to learn from things, prior experiences, things you've
yeah,
done before.
exactly. Yep.
Yeah. So, what should we expect from Rain in this context of what we're talking about over the next couple of years? What's exciting coming?
Yeah, so on the immediate horizon, I mentioned this memory wall or von Neumann bottleneck, this idea that, CPUs and GPUs, they spend the vast majority of their time and energy simply just moving data between where the memory is stored and where the processing happens. At Rain, we're building a processor that unifies memory and processing, that does the computations inside the memory so that you can really dramatically reduce the amount of this data movement that contributes to latency and it contributes to power consumption. And so our first products are going to be targeted towards edge devices. So relatively small, like convolutional neural networks to do image processing. Like maybe you would run this in a drone or some other use case where you're power constrained, like robots. Um, and maybe you want to do speech recognition as well in a low power footprint. So this is the type of chip that could be integrated into, a VR headset or cell phone or something like that, that could reduce the power consumption and latency of running these types of computer vision models, speech recognition models. Also, we want to enable these devices to be able to do training, right? Like there are a lot of cases where, I'll give you an example for like drones. There are some companies out there who want to do like inspection of critical infrastructure in an automated fashion using drones. So a lot of American infrastructure is not doing so great. We want to be able to repair and monitor that infrastructure. It's just really expensive because you have to have people go out and do
Mm-hmm.
this. But if you can automate that, you can improve the quality of the infrastructure, I think, by quite a lot. The problem is that, when you train a neural network to do image processing, right? The data that it trains on, in the data center is invariably going to be different from the data that it sees in the real world. And maybe this is just due to the fact that when you put a camera on a drone, it's a little shaky, right? Or it's blurry because it's moving quickly, or it's operating in the rain and it's, not a lot of its data has been in the rain, or there's blur, or there's a water droplet on the camera, or some dead pixels, right? All of these changes really degrade the performance of the image recognition system, right? But if you can have adaptation, if you can build in the ability for the network, for that chip to adapt to its environment in real time on the fly, you can recover a lot of that accuracy. And this sort of drop in accuracy from, it's called domain shift between its training data and the data that it's seeing in the real world. Um, this is a big problem that limits applicability, limits a lot of applications. And so this is another thing that we're trying to solve, is give these systems the ability to adapt to their data on the fly and try and prevent problems from domain shift. But that's our immediate product. We are working on bigger and better things as well. So I lead the Frontier Research Division at RAIN, and our goal is to build, multiple order of magnitude more performant systems for significantly larger neural networks, like transformer architectures, LLMs eventually. And as I mentioned, one of these breakthroughs in DRAM, I think, is one of the keys to this. There's others, some memory technologies on the horizon, like resistive RAM and things like that, that we're interested in. But, we're keeping our ear to the ground and seeing what innovations are popping up and incorporating those and developing our own innovations to power what I think is going to be the next, like the real wave of commercialization of these systems, because it requires vastly higher levels of compute efficiency. right? They're just too expensive computationally right now to really be too practical.
Yeah, what you're doing is super important. I mean, I think that the software side gets so much attention because people can naturally use it and they can feel it and they've experienced ChatGPT, but the reality is the brain is the hardware. I mean, that's really where it happens, right? I mean, the models
Yeah.
are fun to think about and they're going to evolve a lot per our conversation today and very quickly. But getting the hardware right and getting it in place and having it be efficient is, I think, underappreciated.
I completely agree. I completely agree. And we've seen, we're maybe a great new architecture will come out, and will show us that you can get, 1,000x improvements from model architecture alone. But I mean, just from what we see in the brain, the brain has got like 100 trillion synapses, I
Mm.
think, right? 100 trillion parameters. Like, I think that, model architecture improvements can only get us, 1 to 2 order of magnitudes worth of improvement, maybe 10 to 100x. But hardware, we are more like 4 to 5, maybe even 6 orders of magnitude away from biological brains in terms of the actual hardware. So there's many, many more orders of magnitude more to be gained from hardware than architecture improvements. And I think hardware, changing the way that we do computation in these processors, doing computations inside memory, being more brain-like. I think that's the future of AI.
Absolutely. Well, you guys are working on the right problem. Jack, you're the right one to be leading the charge on it as well. This has been, I think, super enlightening just to think about where we're going and how fast we're going, and then ultimately, how rain plays into it. So thanks for coming and talking with me today. And I'm sure we will do this again because there's so much more to
Yeah.
talk about.
Yeah. Thank you so much, Doug. Really appreciate it. And thanks for having me.
Thanks.